between them
90.
90 degrees. So that's one thing you want to practically have knee jerk. I mean, the minute you see that, that's immediately what you know. Give another vector orthogonal to this. Now, this is one of these problems. There's infinitely many answers. I haven't done this, but so what are you looking for?
A times 1 plus b times 2 plus c times 3 is 0.
-3, but yeah. I mean, you're just looking for something to dot with this to get 0. And I should probably specify a non-zero vector. Okay. Easy way to do that, so some answers. Easy way to do that is to pick two of the coordinates, swap their location, and change the sign on one of them, and put a 0 in for the third component. You see what that does? Or you might have 0, 3, 2. Or you might have 1, 1, 1. That works. You know, just something where the dot product is 0. And if you were asked to make it a unit vector, give a unit vector orthogonal, then you would divide by magnitude, because that wouldn't change the orthogonality. So all I've done is, the easiest way is to flip two of the components' position, changing the sign on one of them. And then 0 out the third. That will give you the orthogonality, but you can always check -2 plus 2 plus 0 is 0. Okay?
Does it matter which one you're changing the sign?
No.
So you could
No,
make it
no,
0,
because any
-3.
multiple of it is still going to be orthogonal. So you can check out 2, -1, 0, in which case you would get 2, -1, 0. The nice thing here is that you're looking for something orthogonal, in essence, think perpendicular. You haven't drawn a single picture, and yet it's fairly easy to find vectors that are, in fact, orthogonal. Okay? Give a vector parallel to the line. In 2 dimensions, parallel would be indicated by same slope. The counterpart of slope in 3 dimensions is the direction vector. Okay? And the direction vector here would be, peel off these coefficients. That works, or any multiple of this. So you could give -8, 16, 10, and that would be perfectly acceptable. It's just any multiple of this. It's going to be a vector parallel to my line. If you were asked to make it a unit vector, you would divide by its magnitude, whatever square root of 4 squared plus 8 squared plus 5 squared is. Okay? If A dot B is less than 0, then the angle between the two is
Acute.
bigger than 90 degrees when you put those vectors tail to tail. So you have an obtuse angle bigger than 90 degrees when A and B are tail to tail.
That's not a direct correlation, is it? Like if you got negative 11, it wouldn't be 180 minus the 11 to give you the angle 169.
What's minus 11?
If your angles, you're getting,
It's not telling me what the angle
because
is.
you have to plug it back in.
You have to know, yeah. What I could have done is say, given you two vectors and say, find the angle between them, in which case you get that cosine inverse.
Okay.
Okay? A dot B, is it positive, is it negative, is it 0?
Negative.
It's negative. The reason being, if I redraw, that would be A, and if I place B tail to tail, and that's the key, because if you place them head to tail, the angle's less than 90 degrees. But you place them tail to tail, that's bigger than 90 degrees, and so the conclusion is A dot B is negative. These are little problems. Every one of them could be test problems. Just, kind of running through. Okay? It's really amazing, but there is very little in this chapter that we will not, at some point in time, make use of. Many things more than once. It's not calculus per se. We haven't integrated anything, differentiated anything. I haven't even talked about a function. But we will be using these, so. Okay, questions here? Okay. The magnitude of V is square root of 26. So this is a unit vector in the same direction. I don't care if you distribute that into the vector or not. That's of length 1. And then once I've shrunk the vector down to length 1, or possibly expanded it, I multiply by my desired length. Okay? If I want a circle of radius 6 centered at the origin, it's going to be some combination of cosines and sines. This is not the only answer. You may have other answers. I mean, there's infinitely many different possibilities. But you're going to have a 6 cosine of something and a 6 sine of the same angle. I started off with 6 cosine for my x, and notice at t equals 0, cosine of 0 is 1. So I'd be started off with an x-coordinate of 1, sine of 0 is 0, so I'm in fact starting out like this. If you look at graphs of the cosine and the sine function, cosine function looks like this, just at the very beginning, and the sine function looks like this, just at the very beginning. For t values, just a little bit bigger than 0, actually quite a bit bigger, but initially cosine and sine of t start out positive. If I want my rotation in this direction, I need my y values to be negative. So I throw a negative in front. That'll get the rotation this way. I want a half of a revolution. Go through 1/2 of the period of your trig functions. T runs between 0 and pi. Now, these things can change depending on what you do with this.
The negative would have to be at the x in order for it to be pi over 2 pi. Is that right?
Say it again.
The negative would have to be with the x instead of the y in order for it to be pi over 2 or 2 pi? Or is that just like a too quick of an assumption?
Okay. If you did this, negative, I don't know if I'm going to answer your question, so if I don't, just make sure. Is this what you're looking for?
Yes.
Yeah. If you did this and then y is,
6 is positive 6. Sine.
okay, so if you do this, if you let t equal 0, you'd be over here, which is not what you want. So you started at,
Well, I did 6 cosine t, negative 6 sine t, but I did pi over 2, t greater than or equal to
oh,
pi
you
over
did
2.
these two?
Yes. But I
Oh,
did,
okay, so
pi-
you went pi over 2
Yes.
up to
2 pi.
2 pi. Not going to happen,
No.
okay? For one reason, that's 3/4 of one cycle. It's going to give you 3/4 of the circle. But notice,
Oh, no, I'm sorry, I did do pi.
yeah, okay.
Okay, sorry. Yeah, because that would...
Well,
I-
okay,
go
you
to-
need this really to go up 1/2 of a revolution, but it's still not going to work. Because if you look at what cosine of pi over 2 is, that is 0. And sine of pi over 2 is 1.
My apologies, I said it incorrectly. I actually did t greater than or equal to pi, less than or equal to 2 pi.
So pi less than or equal to t less than or equal to 2 pi.
Yes, ma'am.
Okay, so if we do this, cosine of pi is -1. And that would put you with an x-coordinate of -6. So if you wanted this for the restriction, I'd start off like
Yeah, it
this.
has to be that. Okay.
And I still have to make adjustments on the y and figure out the signs.
Okay.
Okay? So there's all kinds of different quirky things. You have to make sure you begin and end at the same place. And keep in mind, you do have on calculator, if you go to that mode, the function mode, you can always put it in parametric mode. It takes some time because you got to go into the viewing window and set the viewing window both for however big you want your XY screen to be, but also the parameterization on T, where you want it to begin and end. But if you do that, it will go in, starting at whatever the point is, and it gives you an added check. Okay? Okay, any questions here? Okay. There was one type of problem I didn't go through, the thing with the vectors, but before I run that through, questions out of 12.3 other than the force kind of questions? Any problems? Okay. Before I mess here, if I told you that this was a force vector. And if I told you this angle, for instance, was 20 degrees, and I said the magnitude of F is, say, 3 newtons. Write F in component form, 2 dimensions. And as far as I'm concerned, no need at all to go punching the numbers in. If you punch them in wrong, I'm gonna look for this anyways. And if you don't have this and you punch them in wrong, you're kind of screwed because I'd have no way to check. So, okay. Be careful. First of all, magnitude to be 3 newtons, I need 3's in here. Trig, that's the cosine and the sine. But just watch, if you're given an angle like this, 20 degrees, and if you write the components with cosine and sine of 20, you have to adjust your sine, the SIGN sine, because you're going in the negative x and the negative y in this instance. If you want to avoid that issue, then use this angle, which would be 200 degrees. And then you don't need to worry about pluses and minuses. Okay? So 2 points to this. One is magnitude. That's going to crop up in problems. They're going to say a vector has such and such a magnitude. It's, you know, sitting right there. That's part of the problem. You could pull the 3 out front if you want. Okay. A sample problem that I did not do last time is problem 78. This is on page 6, oops, actually 686. So they have, I guess they call it a wagon or something, but they have an object. It's 40 kilograms and it's dangling from 2 wires that conveniently each are at a 35-degree angle here with the horizontal. Now, I will say this is the kind of thing that'll bug me. The book actually calls both of these vectors F. They are not the same vector. They're pointing in different directions. And that, I don't know, that just bugs me when, I don't know. Yeah, I mean, if I'm a student, I'm looking at that, I'm going to say, hey, those are the same vector, but wait a minute, they're not. So be aware of that. I labeled them F1 and F2. They both have the same magnitude. So I'm reading between their lines there, that they're writing them both as f. So I will say, these two vectors have the same magnitude. They're both at these 35-degree angles. I will call that magnitude f. Now, this is very typical in a lot of cases that people will use the same letter for the vector as they do for the magnitude. You tell the difference because that doesn't have a vector sign over it. So that means I can write f1 as f cosine of 35, f sine of 35. And I can write f2 if I want to keep with the 35-degree angle. Just make sure you throw the negative in front to get it in the negative x direction. Or whatever 180 minus 35 is, you could use that and then not have to worry. Your object has an additional force acting on it due to gravity, and that force is going to have magnitude 40 kilograms times your gravitational constant. And if we're working with kilograms for our mass, then that's your gravitational constant. The object is not moving. It's the difference between statics and dynamics, which I think you guys have to each take. If it's not moving, what that means is that these three vectors add up to the zero vector. So all the forces in the horizontal and the vertical directions, all the component forces sum up to zero. If you look at the x components, well, they add up to zero. I don't get any information from that. But if you look at the y's, you get this equation. These guys are the same. So I get this, a little equation. You're just going to end up solving it for f. So what, minus 20 times 9.8 over sine of 35 degrees. So threw the minus 40 over and then divided by 2. If this were a test and you left your answer like that, that would be perfectly fine by me. If you multiply it out and punch it in wrong, if you're in the wrong mode, radians and not degrees or whatever, the first thing I'm going to look for is this. And if I don't see that, there's nothing I can do about partial credit or even full credit. But if I see this, I'm going to say, you guys punched it in wrong, so what? I mean, it's a so what if the bridge falls down, but we're not building bridges in here. Presumably, if you were, you would have time to check everything over 5-6 times.
Is the top portion not positive? When you move it over?
Oh, I don't know why I didn't do that. I think I was too much teaching of low level. I'm sitting here stressing about, will you guys know how I got this if I just write it down? And the minus sign got lost in the shuffle. Okay? So, these are problems. There's a few of them in the book, and they're worth looking at. Probably a lot of you have already seen these types of problems in other places. Okay. Questions? Okay. All right. So I guess that puts us into 12.4. Before I do 12.4, let me run through determinants. Some of you already know how to compute these things. If you've taken linear algebra, you certainly do. Engineering people, if you're working with a 3x3, there is a shortcut method of doing it. And that works just fine as long as you're with a 3x3. I think it is mentioned somewhere in the book. I forget where, but everybody in here, if you haven't already taken a linear algebra, will have to take either the 1 hour or the 3 hour, except maybe you.
I'll probably take that.
Yeah. So, determinants are one of the topics in there. The shortcut method that you may or may not have seen in an engineering class or a physics class will not work on bigger determinants. So I usually take this time to just run it through with you guys, and it's obnoxious. It's very difficult to write down the formula for everything, and it's best to watch. And if you want to do the shortcut, if you know it, or you get somebody to show it to you, fine. I don't care. The determinant that we are going to be working with is not going to be able to be done on a calculator because it's not all numbers. That's the one catch. Okay, but it's not hard. So, first of all, an array of numbers is called a matrix. And all you need to do is to be able to compute some determinants. I'm not going to be testing you over this, but I am going to give you the vocabulary so I can talk about it. So, if you have an array of numbers, meaning numbers listed in row and column form, that's called a matrix. Computers eat these things up. Okay, it's a nice organized way to put information in. This particular matrix is called, or is referred to, as a 2x3. This is the matrices dimension. When we give dimension, the first number is the number of rows, the second number, the number of columns. And I'm lame, I have trouble remembering things, so my mnemonic is RC Cola, which I think is rapidly losing any meaning because I don't know of anybody that ever drinks it. But that notwithstanding, RC Cola does it for me. Okay? Row number first, column number. If you have a matrix, it is, if I list out the numbers, denoted with rounded parentheses. Usually, people will call the matrix using a capital letter. If I want to refer to it more generally, you might see people write this. A sub ij. And a lot of times they'll use the small a of the matrices, capital A. The I and the J stand for location of my elements in the matrix. So for instance, with this particular matrix here, if I said what is 2, 3, that would be the number in the second row, third column. So second row, third column, that would work out to be -1. Okay, so when we do this, it's in the same order. When I use these subscripts, it's row number, column number. Okay? You don't have to copy these numbers down exact, but this is what I would refer to as a square matrix. It's a 3 by 3 matrix. The number of rows matches the number of columns. And these numbers right here, that's the diagonal. So people use these things to do a bunch of stuff. One of the things they'll use it for is solving linear systems of equations, which usually is a pain in the neck to solve such things, especially if they're bigger than a 2 by 2. 2 equations, 2 unknowns. And you'll pick that up in your linear algebra. We define something called a determinant of a matrix A only when our matrix is square. So people are referring to determinants. They're not going to be referring to taking the determinant of this matrix because it's not square. Only square matrices. If I write using absolute value signs like this, that's typically the symbol, or people will write this. That's the symbol or symbols that are used to represent the determinant of A. Absolute value, you could think about it as a magnitude, and you're not at all far off, although seeing that connection is a little bit stickier. Not to worry, but it is that same symbol as magnitude for a vector and magnitude of a number. You can also talk about magnitudes of functions and all kinds of things. So you'll see this symbol used again. The definition of a determinant is recursive. So that means, who's the computer gurus? You guys know recursive bootstrap.
Well, if you, in regards to programs, like in functions, like a recursive function is a function that calls itself and does itself over again, so it's self-replicating.
Yeah, okay. So the idea is I give it some input and it uses that input to generate out some more stuff, and then it uses that stuff to generate out back, just keeps going back. This is going to be a recursive definition. So what I'm going to do is to define the determinant of A when A is a 2 by 2 matrix. So if A is equal to this matrix, we define determinant of A to be AD minus BC. This diagonal first, multiply, minus this diagonal, multiply. These are very easy to compute, 2 by 2. Okay? Define magnitude, or define determinant of A for 3 by 3s. And this is going to be tedious and weird if you've not seen it. So, I'm going to do this with numbers, not in general. So let me start with this. So that's going to be my matrix, which I conveniently put on the very end of that page, meaning I will have no room. So let me copy it over. And I want to take its determinant, so I'll put the vertical lines around it. And I'm going to expand along the third row. I have to explain what that means, but you'll see. So I'm going to go across this row. So I'm going to pick up the first number, 3. So that number 3 is in position, so it's in the third row, first column. Three plus 1 is 4. That happens to be an even number. What I'm going to do is write down 3. Pretty weird. Then what I'm going to do is to mentally block out the row and column that that number was in. That leaves me with these 4 numbers. Here's the recursive part of this definition. I will take the determinant of the remaining 2 by 2. Proceed to the next number. So -1 is in position, so it's in the third row, second column. 3 plus 2 is 5, that's odd. So multiply that entry by -1. So what I'm going to do is I'm going to generate a series of plus minuses type of deal. So what I'm going to do is I have a -1 I want another minus in here so that this will actually, in this instance, become a plus. I wipe out the row and column that -1 is in. And that's going to leave me with 4 numbers. 0, -2, 3, 5. I will take that determinant. Move on to 5. 5 is in position 3, 3. 3 plus 3 is even. Don't change the sign of that entry. Just leave it be. So I'll go +5. Wipe out the row and column that 5 is in, and I have this. This is the recursive part of the definition because I've reduced my 3 by 3 determinant into a bunch of 2 by 2s. So if I continue, this would then be equal to 3 times, okay, so this is 4 minus 4, so that's 0, plus 1 times,
Yeah, for just 1 second.
Yeah.
Yeah, the row and column for -1 would be 3, 1, 0, -2.
did I foul that up? What?
It's from the third row,
So if we block out the second column in the third row, it leaves 3, 1, 0, -2, right?
yes.
Okay, I'll take, 3, thank you, because I'm gonna do this in a different order, and I would not get the same answer, and then I would be going, ugh. So is that right? Okay, so this is +1 times, and then this becomes -6. And then +5 times, I guess this is just 12. So 60 minus 6 is 54. Pretty weird.
So the determinant of A is 54.
Assuming I've not fouled up anything in here yet. Now, I'm going to write down this same determinant and indicate the following, or show you the following. It does not matter which row or which column I go down or across. As long as I follow this procedure and I do everything correctly, don't foul up the arithmetic or foul up my result, I'm going to get the same answer, which I always think is really totally weird. Okay, so I went across the bottom row. Let me go down the second column. And this will go quicker because I won't write it all out. If I go down the second column, I begin with -2, but it's in location 1,